a new chapter. If chapter 14 was to do with differentiation of multivariate functions, then it might not surprise you that the next chapter, chapter 15, deals with how do you integrate multivariate functions. So how do you integrate a function of two variables? Well, first the notation changes. Do you notice it's got a double integral instead of a single integral symbol? There's your function, and then we have a generic placeholder called dA. That's just your double integral of the function f of xy with respect to an area called A, dA. Now, this is a very feeble attempt at drawing a 3D picture to show you what you've got. Can you imagine z as a function called, z equals x squared plus y squared, right? Whatever it is, your surface. On the floor, you've got a rectangle. This rectangle here is basically A. And you take this rectangle and you go vertically upwards and it meets the surface. When you get this double integral, that's what they're called, you've just found the volume underneath the curve. It's kind of analogous to area under a curve, right? But now you're going to find volume under a curve. So when you find these double integrals, that's how it works. So let's suppose that I had a rectangle on the floor, where it was they all go. And this rectangle had an x going from 1 to 3 and a y going from 2 to 4, right? So there's my little rectangle. And I have a function, z equals x squared plus y cubed. So imagine there's a surface up here. Can you imagine finding the volume of, it's not really a cuboid, and the reason it's not a cuboid is, would the roof of the cuboid be curved? Right? Because that's where it meets the surface. So I would like to find this double integral. Well, that's what a double integral looks like. There goes the function, dx dy is the notation that we use, which is not a surprise, isn't it? Like dx in normal integration from Calc 2. And here's the function. And then 1 to 3. You will find that it's not uncommon for a lot of textbooks to abbreviate what I just did ever so slightly. 1 to 3, 2 to 4. Now, it's equivalent to this, but if you're going to do that, you have to bear in mind that these numbers are with respect to x, and these numbers are respect to y. So this basically is integrating this function from x going from 1 to 3 and from y going 2 to 4. Now, when it's a rectangular region, it's pretty easy to tell who the x and who the y is just because of the way this is written. Now, we haven't even talked yet about how to calculate that, but let me tell you another property before we even go there. There are two distinctly different ways in which you can evaluate this volume, this double integral. There's the one that I've just written down. Or you can write this one down. And as long as it's a rectangular region, which it is in 5.1, those two things are totally equivalent. Would you agree? Doing x from 1 to 3 and then doing y from 2 to 4 is the same net effect as doing the y's first and the x's second. Would you agree you still cover the rectangle and you still got the function? Okay, let's do one. Me personally, I like to write these things down. Not such importance with rectangular, but see, once we start doing triangular and irregular shapes, this notation helps a lot, in my opinion. So I do it for everything, that way there's no discrepancies. Invisible wall. When you do double integrals and later on triple integrals, you got to do it inside out. And this wall here, ignore that, like it ain't there. It isn't happening, right? Pretend it's not there. So I'll just write them down and that's them out of the way. Darn it in space, nobody caught it. X's and Y's. Oh, shit in space. Sorry about that, I normally switch my phone off. Okay, here we go. Are we happy about X's go with X's, Y's goes with Y? I should have caught that earlier. Right, here goes. If you've never seen this before, you're going to try and pretend you're the first guy to do it. So I'm going to integrate from 1 to 3 with respect to x squared plus y cubed, okay? So I'm going to integrate from x equals 1 to x equals 3, x squared plus y cubed with respect to x. So it's going to go x equals 1 to x equals 3. Okay, let's do the easy one first. Would it surprise you to know that the power rule works quite well and you get 1/3 x cubed? Now the part. What will the integral of y cubed be with respect to x?
Xy cubed.
That makes sense. Y cubed is a constant. 5 becomes 5x. Y cubed becomes y cubed x. Now you can plug in 3. So what do I get? I get 1/3 times 3 cubed, which is 9. 3 here gets me what? 3y cubed. Take away 1 gets me 1/3, and 1 gets me 1y cubed dy.
Does it matter if you integrate with respect to x first, or can you do y and then x?
Well, that's what this up here is saying. It really doesn't matter. If you look at a question and it just looks like it might be less work to do the y's before the x's, then maybe you should switch the order and do that. I think in this question, it's probably going to be ugly both ways, isn't it? I don't see any advantage in swatting a bit. Are you allowed to? For sure. If you want to, you can do it. Let's tidy this fella up a little bit. 9 take away 1/3 is 27 take 1, that's 26/3. 3 take away 1 gets you 2y cubed dy. And isn't that basically a Calc 2 question? Have you noticed, or maybe you haven't, but this is what's going to happen. See, when you do the first integral, the next piece of your puzzle will only have y's in it. There will never be x's left over, and the reason there's never going to be x's left over is because all the x's get replaced by either a 1 or a 3, right? They disappear. So if you ever see an x left over here, you've screwed up somehow. Well, the rules are add 1 to the power, divide by the new power, evaluated at y equals 2, evaluated at y equals 4. And can I just say dot, 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 because isn't it just a matter of plugging in some numbers and getting a, 82, 312, so whatever the thing is. You comfortable about just finishing that off and you're on? Are we good? Now, you can switch the order. This is true. Sometimes, unfortunately not very often, you can do this as well. Suppose your function can actually be separated like this. An example of that might be, can you imagine f of xy was x cubed sine y, right? So now and again, can't you get a function that you could think of as being separate two things that are just multiplied together, right? If you can do that, then you're allowed to do this. Let's show you what that would look like in this case. If you had to do the integral of x cubed sine y dx dy, you can get that answer by finding the integral of this guy multiplied by the integral of this guy. Occasionally that reduces your workload, but it's quite rare to get a function that's written in this separable format. If your function was called x cubed plus sine y, you cannot do this. You can't say, well, I'll call it the integral of this with x plus the integral of that with y. It just doesn't get you the answer, right? Only works with multiplication.
If it were like x cubed y, could you also do that? Except instead of sine y, we would only have the integral of y.
Yeah. X squared e to the y. 4xy. 2 sine x cosine y. Combinations like that, you could do this.
So would it be fair to say you can do this if you would use the power rule to differentiate it? Or not power rule, but a product rule?
It's not even really a product rule in the usual sense because it doesn't have an f-g and an fg dashed.
Yeah,
but you are allowed to separate it.
I'm just saying if you would use the power rule or the product rule to differentiate it, you could use this rule to integrate it?
Yes, you can use this rule to integrate a function as long as that function is made up of two separate x function times y function. You can use this shortcut. That may be your question. Well, let's do one. Let's suppose I wanted to get the integral from y equals 0 to y equals 1 of x equals 0 to x equals pi upon 2. And let's suppose that the function was y cubed sine x dx dy. Now I can just do that the usual way, right? I can simply just integrate that in the usual technique. Or do you see how this is distinct terms, right? Then couldn't I replace this by finding that guy multiplied by that guy? And that would be an application of that property that I've written over here, right? Now, you might call this the product rule, but I don't feel comfortable with doing that, because to me the product rule is in integration. The product rule is really integration by parts. You could call it the multiplication rule if you want to call it that. That might be a name for it. I don't think it's got a name, but if you want a name, that's what you could call it. Right, this fella here, 1/4 y to the 4, evaluated at those points. And this fella is negative cosine x, evaluated at those points. This fella is 1/4 4 to the 4, take away nothing. And this fella is negative cosine pi upon 2, take away negative cosine of 0. That kills one of the 4s, that's 64 times. That guy is nothing.
Where did
That
that
guy's.
4 come from for the y?
Where did the
At
4
some
come
point,
from?
Originally, it was
Wasn't it
1. Then he changed it into a 4.
Oh, okay. Let's make the question consistent. Now I fixed it. Right. This one here is 0, take away, so it's 1. Oh, 64 times 1. So if you took this surface called y cubed sine x, and if you had below it a rectangle where the y's went from 0 to 4 and the x's went from 0 to pi upon 2, so if you took this rectangle and it moved up to this surface, that entire 3D shape would have a volume of 64 cubic units. So double integral in this particular context is finding the volume underneath a surface, a 2D. Right, now, Kevin, you got a thumbs up, so you were happy with whatever way I said it, so that's good.
Could we have found the volumes of the boxes in our min-max problems with this? Or is it not quite geometric like that?
No, it's not. Yeah, the min-max stuff we were doing was to do with finding the maximum height or minimum height of that surface, rather than the volume of that surface. So they're not finding the same things. Okay, let's pick somebody. Let's suppose I want the integral from y equals 1 to 2, and the integral from x equals 1 to 2. And I would like x squared plus xy squared plus y squared. And we're going to do x first, and we're going to do y second, right? This is just a random polynomial. There's no shortcuts to this. Don't you just basically do it in 2 chunks? Chunk 1 will be this fella. So let's see what we get. The integral from 1 to 2 dy. This guy with respect to x. X squared gets me 1/3 x cubed. Okay. Middle term. With respect to x, what does xy squared get you?
X squared, y squared over 2.
Okay, I hear x squared, y squared. Was that over 2?
Yeah.
Yes.
And none wrong with over 2. I'm just going to call it a half. That's just me. Y squared. What does that get you?
XY squared.
Are we comfortable? I think it helped doing partial differentiation. Are we comfortable about y's can be treated as constants? Right, in this case. And this is going to be evaluated at x equals 1 to x equals 2. So let's see what we now got. That's going to be 1/3 to 2. There's 8 cubes. 2 2 is 4. That's going to be 2y squared. And another 2, so that's 2y squared. That's the first one. Plugging in 1, you get 1/3. You get a half of this guy. And one of these guys. dy. So 8/3 take, that's nice. 8/3 take away 1/3 is 7/3. 2, 4. Okay, what went wrong there? There we go. It's better. 2, 4, 5.5, which is 11 halves, y squared dy. You know my usual. Does that look about right? Have I added them, combined them correctly? If I get a thumbs up, I'm moving on. Does that look okay? Right, okay. Can I ... this fella? Wouldn't you just have to do Calc 2 stuff now? 7/3 y, that'll be y cubed over 6, so 11/6 y cubed evaluated at 1 and 2, and you get an ugly fraction and you're finished. Are we good? Do you want me to do that, or do you feel comfortable with filling that in yourself if you needed to?
I'm good with double integrals, like understanding how to compute them, but I'm confused as how to interpret them conceptually. Like, what does the inside integral represent and what does the outside integral represent? Well, with regard to, again, the concepts.
The process of breaking, the whole picture is easy to conceptualize. What you've got is this surface here. So imagine we had, one day I'm going to have a hologram and I can do stuff that I'll never be able to do. But can you imagine this surface being over here, right?
Yes.
On the floor, you've got a rectangle from x equals 1 to x equals 2, and you've got another, and it goes from y equals 1 to y equals 2. So can you imagine there's a little rectangle here. This combined double integral, essentially, can you imagine this rectangle being projected up to the surface? And it will hit the surface at different points.
Yes.
Did screen share freeze for anybody else?
Yeah, he's frozen.
Yeah, I did.
Did he freeze?
Yes, he needs to leave and come back, or just continue on like he's doing.
Oh, my internet connection is unstable. Can you hear me?
You're back.
Yep.
Yep.
Now it can, yes.
I have no idea what happened there. Can you now see the picture, even if you couldn't see me drawing it before?
Yeah.
So what I was saying is this double integral is finding the volume of this solid shape. Now, your question was, what does the first and the second do? They're just a mechanism to get that. I'm not sure it's easy to think of what they're specifically doing at any given point, but it's kind of something like this, but don't quote me on this. Can you imagine taking very thin slices of this thing vertically? So you're finding the area, essentially, of a infinitely thin slice going one way, and then adding them up going the other way. So could you imagine, you could think of a volume as an infinite number of two-dimensional pieces of paper, like a funny shaped book stuck together.
Yes.
And so that's getting the area of one of those infinitely thin pieces of paper cut in the x direction. And then you're adding them all up in the y direction. And so you're sticking them together in a book, and you're finding the volume of what that weird shaped book would be. Does that help in any way to visualize what it's doing?
Sort of. Yes.
Yeah.
Well,
Me
sort of.
personally, I like to figure out what the overall thing is doing, because I can see, you're finding the volume from a rectangle when it meets the surface. It's like the volume under a surface. Because that kind of works with my brain, because, well, it's just like finding the area under a surface, but now we're finding a volume under a surface.
What exactly does this do for us? Because now we know the volume, but why?
Oh, it's the same thing. Why would you want to know the area of something? Well, maybe the volume under that something represents, well, imagine that surface represented magnetism or potential. Then maybe the volume underneath that would represent the total amount of magnetism or the total amount of potential or temperature or what that would be under the surface. Not being an engineer, I don't really care what it does. I kind of like the fact that it just does stuff. But you being an engineer, or if you wanted to become an engineer, you would be able to use double integrals to find volumes under things because evidently engineers want to. That's a horrible answer, but I'm not an engineer, so I can't give you a good one. Analogy. Isn't the area under a velocity time graph distance traveled? Can you see that the area under a curve can represent something you might want to know? Right. So I'm assuming that the volume under a surface could well represent something you want to know. But I can't off the top of my head come up with an example of that. Maybe one day one of you will say, hey, I looked this up and double integrals are used in electrical engineering because they tell them things. Okay, let's try another fella. How about this one? Double integral of e to the power x add y. Okay, now I can do this question two totally different ways. And it won't matter, because both ways work. And both ways obviously give me the same answer, because they work. Let's tackle this just the typical way. So won't you do this guy first? Let's see what we get. Integrate e to the x plus y with respect to x. Well, if you integrate e to the x plus y with respect to x, don't you get e to the x plus y? Think of integrating e to the x plus 5. Don't you just get e to the x plus 5? So that's that finished. You go from x equals 1 to x equals 2. dy. Are you comfortable with e to the x plus y is just e to the x plus y, right? Now, that's going to be the integral from 0 to 1. If you plug in 2, you get 2 plus y. Take away, if you plug in 1, you get 1 plus y dy. Well, integrate e to the 2 plus y is the same thing as e to the y plus 2, so you don't get anything. And you integrate this one, and you don't get anything that interesting. And you evaluate it from 0 to 1. Now you plug in 1, you get e cubed. You plug in 1, you get e squared. Take away, you plug in 0, you get e squared. And you plug in 0, you get e to the 1. That guy and that guy, let's see what we get. I have e cubed. Take away 2e squared plus an e to the 1. We're all comfortable with that? Any questions about this particular question, the one I've just done? Okay, here goes. I said there was 2 ways to do this. And I'm not saying this is a better way. In fact, it might be actually a little bit more work. But isn't e to the power of x plus y e to the x times e to the y? And that means that, can't I split this up? Oops. Can I split them up into a y guy times an x guy? And this fella is e to the y evaluated at 0 and 1. And this fella is e to the x evaluated at 1 and at 2. This guy gets you e to the 1, take away e to the 0. And this fella here gets you e squared, take away e to the 1. And that times that gets you e cubed. That times that gets you e squared. That times that gets you another e squared. And that times that gets you plus e to the 1. You see, you end up with the same answer. Are we okay with that question? Which way would I choose? Me personally, I'd probably choose that one. It just seemed to me, this one here, seemed to me just to be a little bit less thinking involved. It's just a process. Here you had to do some tweaking to make it work. So that's just my opinion, that this is a little bit less work. Okay. Here is one off the homework. The integral is going to be y equals 0 to y equals 2. And the integral is x equals 0 to x equals 1. If you're wondering, this is a version of question 2. Okay, I want to find this double integral. So let's figure out what this piece is first. So it's going to be an integral from y equals 0 to y equals 2 dy. X plus y bracket squared. I want to integrate that with respect to x. Two different approaches, again, both work. Right? Any ideas of how I could do it? I have two different approaches, pick one, or tell me one.
You could FOIL it out and go from there.
Agreed?
Yes.
I'm totally fine with that, and it works. I'm just not going to do it, because I only want to do one of the two. But nothing wrong with that. Go ahead and do it. It works perfectly fine. Great at method. None wrong with it. Okay, I said there's two. So maybe the second one's a little bit less obvious. And I'm not saying this is the better way of doing it. I'm just saying this is another way of doing it, right? That's all. Last few seconds. It's okay to get it wrong. If they're a half-formed idea, just tell me what it is, and I'm.
Could you do a U-sub?
God, that is a very interesting thought. I'm not saying that won't work. I just don't want to try it. That's an interesting thought. I'd have to think about that. I'm pretty sure it would work. I'm just choose not to do it. Okay, here goes. I'm just going to look at that, and this is sort of a kind of connected to the chain rule. See if it was just x squared, wouldn't you get a third x cubed? So in this particular case, would it seem reasonable that you could just get 1/3 x plus y cubed? Now, if it was 2x, that would be different. See if there was a 2x plus y here, wouldn't I also have to multiply with an extra half? And that brings up the chain rule technique. That would actually probably have helped in that case. But in this case, you're going to plug in x equals 0 to x equals 1. So it's going to be the integral from 0 to 2 of, well, when you plug in 1, you get 1/3 1 plus y cubed. And when you plug in 0, you get negative 1/3 y cubed dy. And now we have this guy to deal with. Great. Plug in 1, you get this. Plug in 0, you get that. Okay, now we need to figure out how we could integrate this. Couldn't we FOIL this out and then just collect like terms and figure out what we get, and we'd end up with some kind of, actually you'd end up with quadratic because the y cubes would cancel. And that is a sensible technique. Or can't we just bite the bullet and keep going? See what happens. If you add 1 to the power and divide by the new power, won't you get that out of this fella? And if you add 1 to the power and divide by the new power, you get that. And then you evaluated it, y equals 2 and y equals 0. So you'll have 1/12 3 to the 4, take away 1/12 2 to the 4, minus a whole load of nothings. So that's 81/12. Take away 16/12, which gives me, I believe, 65/12, or thereabouts.
I think it's not -0 because you still have the 1 plus y.
Oh, okay, minus a 12th.
Okay.
64, 32 sixes, 16/3 or thereabouts. Right. I should probably have said ... there and saved a whole load of grief. We feel cool about this integration process now, these double integrals. As long as these are numbers, you can choose to do them in any order that you like.
We do
and it
roll.
works. Sorry? Oh, roll, yeah. Let's do the roll. So wait a few moments while you all say hi. Okay, last one. Y equals 1 to 2. X equals 1 to 4. Okay, there isn't any shortcut, just go with the flow and see what we get. So y is going to go from 1 to 2, going to be a dy over here. Let's see what we get. X over y with respect to x. Integrate x over y with respect to x. It's going to be a little bit messy, isn't it? What will it be?
1 over y.
That's differentiation.
Are
It
you
would
asking
be
for
1
the
over.
first or the second one?
Right, so this fella here, the x over y.
Be x squared over 2y.
Agreed. Add 1 to the power, divide by the new power. Now, y over x, be careful. With respect to x,
Natural
what's
log
it?
of x times y.
Okay, agreed. And then evaluate it to x equals 1 to x equals 4. And so what do we get? We get 4, so that's 16 over 2, so I believe that's 8 over y. And you plug it in here, and you basically just get that. And then you plug in 1, you get 1 over 2y. And you plug in 1, oh good, that's 0, right? Log of 1 0, so it don't matter. So you get that. So we get 1 over 2. That guy and that guy have to be converted to share the same common denominator, which is 2y. So that's 16 over 2y. Take 1 over 2y. And that's why I got 15 over 2y. And be really, really careful about this fella. This guy here is ugly, but for a totally different reason. 15 over 2y can also be written like that. And it's maybe a good idea to write it like that, because if I want to find the antiderivative of this, think of that as being a number you can forget about for a minute. Isn't the answer 15 over 2 natural log of y? If you're not careful, can you see that you might misinterpret the antiderivative of this? Like, I don't know, like that mistake. Can you see why someone might come up with that? It's wrong, but I can see why you might see that. So this fella is 15 over 2 natural log of y. Different problem. What's the antiderivative of this guy, y log 4, with respect to y?
1/2 y squared natural log of 4.
Agreed. And at this point, I'm just going to say ... because it's some ridiculous combination of various logs, isn't it? You should always tidy up your answer style points as much as possible. So don't leave your answer, I'm making this up, but don't leave your answer as 7/2 log 4s plus 1/2 log 8 or something, right? Just imagine that's what you got. There is some work you can do with logs. You could, for instance, pull out 1/2 if that had happened. And you got that. But can't that be called that, for instance? Actually. Something like that. Be on the lookout for just tidying things up. There a general rule, never use a decimal. Just basically never use a decimal, unless the question says to 4 decimal places. Then you know it has to be a decimal. Always try and make your answer look pretty. That one's not very pretty, but that was a random question I picked. Okay, guys, it looks like we're finished.